Hello everyone, myself Pranay Sarkar and you are watching ChemPro YouTube channel. Please watch the complete video and don't skip. I promise you will get extra and learn the topic like never before. Today our topic is Julia Olefination. Then let's start. Julia Olefination reaction. This is a regiospecific and a connective reaction, and the alkene is formed by joining together two separate fragments, and the reaction undergoes with a sulfone stabilized anion. Okay, so it is a regiospecific reaction and a connective reaction, and here two fragments, that is this fragment and here this fragment R2C. These two fragments are connecting with each other and ultimately form an E-alkene, and exclusively an E-alkene. Okay, and the reaction undergoes with a sulfone stabilized anion. Now the reaction has three steps in the mechanism. So the first step is carbon-carbon bond formation. Second step is O acylation, and the third step is a reductive elimination. So to understand these three steps, we have to consult the mechanism first. So for that we have the alkyl phenyl sulfone. Okay, so this is alkene phenyl sulfone. Here it has two hydrogens, and these protons are very acidic due to the minus high effect of the SO2 pH. Okay, then it will undergo with a good base, that is butyl lithium, or we can use here like LDA in THF or ETMGBr in THF, etc. So the butyl lithium takes up the proton first and makes an metallated alkyl phenyl sulfone. So we can have from this, that is here SO2 pH, and here we can get a negative along with that and Li positive. Okay, this is the first step. Now second step is it will undergo reaction with the given aldehyde. Now the negative charge will attack the carbonyl carbon and makes a O negative. So from this we can have, here it is R1, here it is R2, now it is OLI, and here we can have SO2 pH. So here the step, that is carbon-carbon bond formation. So here it is a carbon-carbon bond formation. Now the second step, that is O acylation. So for that we have the CH3 CO Cl, and the O negative will attack this carbon and makes the Cl minus to leave this moiety. So from this we can have this, that is here we can have R1, here it is R2, this is O CO CH3, or we can write it as OAC, and here SO2 pH. Okay, so we can easily say that this is the O acylation part. The next step is reductive elimination. So for that we have the reagent NaHg, that is sodium amalgam, along with MEOH or ETOH. So for that we have to write the SO2 pH like this. Okay, this is SO2 pH, and here it is R1, this is OAC, and this is R2. So now one sodium will donate one electron to the SO2 pH. So it will be like this, okay, and makes a sulfur radical. Okay, so from this we can get like this. Here it is R1, R2, this is OAC, and here sulfur, O negative, Na plus, here double bond O, and here it is pH, and there is a radical. Okay, now the second Na will react, and so it will make another O negative, another oxygen into O negative, and makes it like your pH sulfur, O negative, Na plus, like the previous step. Okay, here it is OAC, R1 and R2. Now here we can have a lone pair of electron on the sulfur. So in this step this will make a double bond, and the bond will break and makes it a anion. Okay, so from this we have, here it is R2, here OAC, here negative, and here it is R1. So now this anion can form two types of conformer. So first one is where R1 and R2 are syn to each other, and the second one is where R1 and R2 are trans to each other, and here it is OAC and this is negative. So from this we can just have that these R1 and R2 groups are bulky alkyl group, so they will repel each other. So this is a unstable anion. But these R1 and R2 are far apart to repel each other. Okay, so they do not repel each other, so this anion is very stable, and in this anion it will make the double bond. So from this we can just get the desired 100% E-alkene product. Okay, so the product will be like this. Here it is R2 and here R1. Okay, so this is the E-alkene product. So this is the mechanism. Okay, at first the CC bond formation, then second step is O acylation, and the last step is what? The reductive elimination with the sodium amalgam. This reaction has several types of advantages, but along with that it has a big disadvantage. Okay, and that is this reaction has to follow three separate steps to make the desired product. So this is a three-step reaction. So now we have to make it one-pot reaction or one-step reaction. So for that we have to need a modification for this reaction. So what is the modification? So the modification is we have to replace the SO2 pH or the phenyl sulfone part from this alkyl phenyl sulfone. Okay, so for that we can use this heterocyclic moiety, that is a tetrazole moiety or phenyl tetrazole moiety. Here it is a double bond, here it is a double bond, it is a SO2. Okay, and here it is R1. Okay, so we can just change the SO2 pH part with this heterocyclic moiety. This is the modification, and along with that we have to use the strong base, that is KHMDS, or we can call it like potassium hexamethyl disilazide, that is Me3Si whole twice, N negative and K positive. This will be the reagent. So now we have to know the mechanism. So for the mechanism, we will call this big modification part as PtSO2. Okay, we will call it PtSO2 for the mechanism part. So now let's check the mechanism. We will write here the PtSO2, that is the heterocyclic moiety, and here we can have the R1. Okay, and now the reagent is Me3Si whole twice, N negative and K positive. So this N will take up this proton, okay, this proton, and makes it a negative. Okay, so from this we can have PtSO2, and here we can have the negative. This is R1. So now this will react with the given aldehyde, that is R2CHO, and this will attack like this, okay, like the previous mechanism, and makes it a O negative. So from this we can have the PtSO2 along with here R1. Now this is R2 and here O negative. Now we can write this like the elaborate structured form, that is the tetrazole structure, N, 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 here it is N, H. So here it is the sulfur, double bond O, double bond O, and now here R1, it is R2, and here we can have the O negative part. So now, and here also two double bonds. So now this O negative will attack this, and this double bond will break. So from these we can have this product. This negative on the nitrogen will make it a double bond, and it will break to the sulfur, and from this we can have this moiety. So now here this O negative will make this double bond, and this part will make a anion on the carbon. So now here we can have the anion. So this R and R have to be anti to each other. Okay, so here the negative will make this double bond, and this will leave the moiety. So from this we can have the desired product, that is R2 and R1, okay, anti to each other, and this is a E-alkene, exclusively an E-alkene. Okay, this is the E-alkene. So this is the overall modification of this reaction. Okay, this is the whole mechanism. This is the whole mechanism for this reaction. Now let's check some examples or some problems. So first one is this problem, and this problem is from Clayden. Okay, so for this we have to just look at two sides. Okay, so first side is this carbon, okay, this carbon and this carbon. So now we have to just make a double bond between these two carbons, and this pH and this whole moiety will be anti to each other. So what will be the product? The product will be like this. Here this is the moiety, and here this is the carbon, and we have to make a double bond with this carbon with the pH. Okay, and the pH should be at anti position. Okay, so now this will be the desired product. So we have to look upon only this carbon, and this carbon, and the pH and the whole moiety will be at anti to each other along with the double bond. Okay, now let's check the second example. This is the second example. This will also from the Clayden. So in this reaction we have to look upon just on this carbon and this carbon. These two carbon will make a double bond, and this whole part and the R will be anti to each other. Okay, so the product will be here, this part and the R is anti to each other, and here this is the carbon and this is the carbon. Okay, and they will make the double bond. Now let's check the third example. This is the third example, and this example is from Carruthers. Now here we have to see on the this carbon and this carbon, they will make the double bond, and the Me and the whole part will be trans to each other. So the product will be, so this Me and this part are trans to each other, and this carbon will make the double bond. So this is the product, and the problem is from the Carruthers. Now the fourth example is, so this is the problem, the fourth problem, and this is also from the Carruthers. Okay, so in this problem there are two bulky groups or two bulky substrates are given, and these are the reagents. Okay, these are the reagents, but we should not be afraid of these big structures. So here we have to only look the two carbons that will make bond or the double bond, that is this carbon and this carbon. These two carbons will make the double bond, and the whole other part of the molecules, okay, this part and these other parts will be trans to each other. Okay, so let's make the product. So this will be the product. So from this product we can say that this carbon and this carbon makes the double bond, and the other parts, that is this part and this part is trans to each other, and this is the desired product. Very simple. Now let's check a problem from the Zweifel, that is the fifth problem, and this is a very important problem. So this is the fifth example. So here there are two steps in this reaction, and for that we have to make the J1 and J2. Okay, so here the first step that is given, this will make the reaction with PHSCH2Cl. Okay, so here it is PHSCH2Li. Okay, so this is Li positive and this is CH2 negative. So this will attack the carbonyl carbon and makes it a O negative. So from this we can have this, okay, O negative, and here it is CH2S pH. Okay, and here it is given that aqueous HCl workup. So after workup, this O negative will be OH. This is OH, and here we can have the S pH. Now the reagent is given that MCPBA. This is the second reagent, MCPBA, and this will oxidize the sulfone. So from this we can have, this is OH, and from this we can have SO2 pH. And the third step, that is POCl3, will make the dehydration of the alcohol. So we can have from this, that is, here it is a double bond and this is SO2 pH. So we can just say that this moiety is known to us. Okay, and this is the substrate for the Julia olefination. So this is our J1. This is our J1. Okay, now we have to go through the second step of the reaction, that is this part of this reaction. So for that we have this J1 double bond and SO2 pH. So after the N-butyl lithium, first we have the N-butyl lithium as base, second is the PH CHO, and third is the Ac2O, and fourth is the NaHG or the sodium amalgam. So for the previous example, we have to see this carbon and this carbon, they will make the double bond, and the other part, that is this part, and the pH will be trans to each other. Okay, so let's make it. So the product will be like this. Here it is the cyclohexene part, and this carbon and this carbon, these two carbons will make a anti-bond. Okay, so we can just write like this, they will make a double bond, and here it is the pH. Okay, so this part, the cyclohexene part and the pH are anti to each other, and this carbon and this carbon will make the double bond. So we can have the product, the ultimate product, that is J2 from this. So this is the very important problem for the CSIR-NET and GATE examination. So this is the problem from Zweifel. Thanks for watching the complete video. If you really enjoyed, please like the video and subscribe the channel to motivate me, and hit the bell icon to get all the notifications. And if you have any suggestion or query, please comment down below.